Hi, today I'm gonna present our project this semester was about robust transceiver design with autoencoder. Here's the reference. So our goal was trying to formulate the problem we will encounter when we try to consider a self-read holographic MIMO system. And our motivation was because the practical usage of this channel system deployments will face some challenges like near field and far field hybrid channel conditions and some strong mutual coupling from metasurface antennas and the imperfect channel state information we might encounter when using the system. So our objective was to design a robust full digital precoders for this system under channel uncertainties using complex optimizations. So let me first introduce our system model and notations. So we assume a flat fading MIMO channel model here as a simplified version for us to test out these ideas. And we assume a linear channel model which was written on equation 1, where the delta H denotes the channel estimation error matrix. So we assume it to be within a ellipsoidal constraint, which was denoted by the set H here, where the matrix B is a arbitrary semi-definite, positive semi-definite matrix. So we consider a downlink MIMO system with single base station having anti-antennas and multiple users with in total k different antennas. So this is our notations here. So the channel model is given by equation 3. So for each data stream k, the corresponding rate for data stream k is defined by this on equation 4. So our goal was to design a robust linear precoder which maximized the overall sum rate of all data stream. So now our problem can be written like this, and we want to maximize the minimum of the sum rate under elliptical constraint channel mismatch and also under power constraint. So let's look into how to tackle this problem. So we first look into this inner minimization problem. We first expand this whole problem into expand the maximum problem into with its epigraph representation like this. And notice that we have an infinitely many constraint on the constraint H here. So we expand this constraint by using the infimum of the rate k. So we rewrite it like this. So if we now look into the inner minimization problem, minimizing the rate over different mismatch within the ellipsoid constraint we assumed. So this problem is not convex with respect to delta k because the rate is not convex with respect to delta k. So to tackle this problem, we transform the rate expression using quadratic transform, so it is now written like equation 16. So by theory, we can obtain the optimal auxiliary variables by this closed form equation. So if we plug this y k star back into the rate, quadratically transformed rate expression, we can get back exactly the same value for different delta k. So here are some notation we predefined for our later convenience. So our next step is to obtain the optimal delta k star by solving the problem. So because after the quadratic constraint, the expression is concave with respect to delta k, so we use the first order linear expansion to upper bound this expression, and so we define the linear upper bound at point delta k in the ith iteration as here. And with some arithmetics, we can obtain the gradient with respect to delta k of this rate rk after the transform on equation 20. So now this problem is convex. We transform the problem using majorization minimization techniques. So the problem is now written on equation 21, and this is now convex. So we can now just solve it. We can formulate the Lagrangian of this problem and then solve the optimal delta k by solving the KKT conditions, and we can finally arrive at equation 25. So now we solved our first inner minimization problem, which was trying to find the minimum of the rate with respect to different channel mismatch delta k we have. So the whole algorithm looks like this. So we alternatively update yk star and delta k star until all different rate for different data stream converges. So now, after solving the inner minimization problem, we can now go back to our original problem here and plug it back the optimal rate, the minimum rate we have by finding the corresponding channel mismatch here. So now the rate is written as this. And we solve this problem by solving the Lagrangian using the gradient method. We can obtain the update equations for primal and dual variables from equation 37 to 40. But in this version, the algorithm 2, the problem is solving this gradient of L2 with respect to Vk was computationally expensive. So to tackle this, we perform another quadratic transform on the rate expression again. So now this was easier for us to obtain the overall gradient. So still similarly, according to the theory, the auxiliary variables can have a closed form equation on equation 42 like this. So plug it back into the quadratically transformed rate expression. We can now obtain the gradient of the Lagrangian with respect to different Vk more easily. So after some arithmetics, we can obtain the update equation for different precoders Vn star on equation 49. So our whole algorithms now look like this. So we first run the algorithm 1 to obtain the optimal channel mismatch that will minimize each data stream. And then after that, we use this channel to alternatively update the auxiliary variable and the precoders we have until the rate expression converge. So after this converge, we update the primal and dual variables using the same expression as we do in the previous version of this algorithm, and we run this until the overall rate converge. And after that, we can have the optimal precoder design that consider the channel mismatch. So for simulation, we run a simple cycle case when we have only one user and we have 32 and transmit antennas here. And for the ellipsoid constraint, because we are using a Rayleigh fading channel, IID Rayleigh fading channel, so in here we just assume it to have a MMSE variance with the confidence level R squared, which was calculated by the inverse of the chi-square. And we have two different SNR expression. One is for the channel estimation SNR, which was written as SNR est here, and another one is the SNR for the white Gaussian noise, which we directly write it as SNR in our later expression. So for this configuration, our simulation results looks like this. So on the left-hand side, we have the equation of the rate under different value of SNR, and we fixed the estimation SNR for the channel to be 0 dB. So we can actually see that there's a nice gap improvement for our robust design comparing to the non-robust design. And on the right-hand side, it's plotted over different estimation SNR under the fixed SNR values. So as you can see, as we expected, for the lower the channel estimation SNR is, we can actually have a better performance gain with our robust design. But as the channel estimation SNR increase, the gap between them gradually gets smaller. And it's worth mentioning that ideally, the robust design should be flat under all different channel estimation SNR. But yeah, probably because some numerical imprecision or some, training data set problems, we cannot have that optimal results. Yeah, so our conclusion is this robust design demonstrates stable and reliable performance across a wide range of channel estimation qualities, validating its effectiveness in mitigating estimation errors. Yeah, so our next step would be trying to integrate a nonlinear precoders into this cell-free holographic MIMO framework, and then hopefully extend it to hybrid field users and near field beam focusing using HMA constraints. And we hope to verify this using some more realistic channel simulations, like hopefully INF or UMA channels used in the standards. And this is my present today. Thank you for listening.